All right, so guys, today, as advertised, we are going to jump into the fun and exciting world of what are called ice boxes. You thought you loved ice boxes. Wait until you see the ice box. Guys, understand that this is actually... So ice boxes, guys, are a universal convention. The AP authors expect them. They look for them. What you're going to find out is that this ice box is actually a creation of my own. You will not see this in other texts. You will not see this in the Princeton book. But guys, I would propose to you that this is the best way to learn to do these because it takes a structure that you already understand and it builds on it. So here's the way today is going to unfold. We're going to start by going where Brandon wanted to go, and we are going to remind ourselves what are buffers and how do they work as buffers. Then what we're going to do is we're going to step out of that conversation for a couple minutes, and we're going to talk about the capacity of a buffer and the effective range of a buffer. It's a little side conversation. Then guys, after that, what we're going to do is we're going to start titrating buffers. Cooper, you got to ditch your phone. We're going to start talking about titrating buffers. And guys, the way that this is going to go is we're going to set up buffers just like we did in the previous assignment. And then what we're going to do is we're going to start banging on these buffers with strong acids and strong bases, because that's what buffers do, right? They resist change when strong acids and bases are added to them. But guys, we're no longer going to talk about it qualitatively. We're going to talk about it quantitatively using ice boxes. So again, buffers conceptually, a little side conversation about capacity and pH range, then buffers mathematically through the lens of an ice box. You ready to go? Okay, so guys, you tell me, when we talk about the concept of buffers, do you want to do it generically or do you want to do it talking about a specific buffer like sodium acetate and acetic acid? Specifically? Okay. So guys, let's do this then specifically. So guys, let's go back and remind ourselves about how buffers function. This is not in the notes. This is a review of what we did last time. So guys, I know you're getting sick of acetic acid, but trust me, it's good to come back to something we know. You notice in the homework, we do things like lactic acid and butanoic acid, but it's always nice to come back to familiar ground. So guys, this is acetic acid. In order to think about this in terms of a buffer, the first thing that we've got to do is we've got to protonate it. And so we do this. And we now represent our acetic acid in its weak protonated form. But understand, this is not yet a buffer. What do we need to do to acetic acid in order to buffer it? Sodium acetate, lithium acetate, we need to add a salt that contains the common ion. When we do, we end up with an increased concentration of this and an increased concentration of the conjugate base. So guys, let's talk. Why do we end up with an increased concentration of conjugate base ion? Because we added the salt, right? Do I need to write down sodium acetate to tell you the salt, or are you just okay? Well, okay, so what we did is we added sodium acetate to this, and adding the sodium acetate increased the concentration of acetate ion. Now guys, why does that also then increase the concentration of this guy? Le Chatelier's principle. When this goes up, it drives the equilibrium to the left, and now we've got lots of both. We've got a lot of this, and we've got a lot of that. So guys, why is it that a lot of this and a lot of that make a buffer? And the answer to that question is best understood by doing this. And guys, do it with me, and this is the way we're going to represent this throughout the year. So now we've got a buffer. And this we talked about last time, but let's go back over it. How do buffers respond to the addition of hydrogen, strong acid, or hydroxide, a strong base. Well, guys, let's talk about the chemistry, but before we do, let's talk about the general idea. So what is the magic of a buffer? What don't buffers do when we add acids or bases to them? Change pH. So where is pH up there on the board? The protons, right? So guys, we're literally keeping our eye on the protons because this is pH. And so the idea is that when we create a buffer, we can then add a strong acid to it, a source of hydrogen ions, or a strong base to it, a source of hydroxide ions. And when we do, this doesn't change very much. That's why we say it's resistant to changes in pH. So guys, let's do the top one first. When we add protons to the buffer, strong acid, when we add protons to the buffer, what chemistry takes place? So who reacts with the hydrogen ions, the acetate or the acetic acid? The acetate. So this is the chemistry that takes place. For every molecule, and guys, check this out, for every molecule of acid that we add, one molecule of acetate ion. For every one molecule of strong acid that we add, one molecule of acetate ion gets converted into a molecule of unprotonated acetic acid. So these acetate ions latch onto the hydrogen ions, get converted into acetic acid. But guys, notice while this chemistry is happening, what happens to the concentration of hydrogen ion? It doesn't change. But then it does change a little. And what happens for it to change a little? Guys, as these acetic acid molecules get formed, what do some of them do? A few of them break apart. Less than 5%, right? But guys, some of them do break apart, and this goes up a little, so the pH goes down a little. But guys, understand the pH going down is the small result of this breaking apart. It is not the result of the strong acid that you're adding directly to the buffer. Does that make sense? Questions? Exactly, yeah. And I like the way you say, and guys, hear this because it's a good way to conceptualize it. It is an indirect result. And what you're going to find out in about 10 minutes is that's what an iRace box allows you to study mathematically. The iRace box allows you to quantify this chemistry and then the subsequent breaking down that takes place later. That's what iRace boxes let you do. So guys, you okay with that? Does that chemistry make sense? Okay, now hit the reset button and let's talk about the addition of hydroxide. Guys, when we add hydroxide, what chemistry takes place? Who latches onto the hydroxide ions? The acetic acid. So this attaches to this, gets converted to this, and what else gets produced? Water gets kicked out of this. But guys, as that chemistry is taking place, what happens to the concentration of hydrogen ion? Nothing. But then why does it change a little bit later? Well, guys, what's happening to the concentration of acetate ion? It's going up. And what does Le Chatelier's principle say is eventually going to happen? The equilibrium will shift to the left. Does that make sense? It'll shift to the left. And as it does, a little bit of hydrogen ion will get gobbled up, reestablishing the equilibrium as all of this new acetate ion goes this way. And as that equilibrium is reestablished, a little bit of this will go down and the pH will go up just a little. Yeah. No, the volume change due to the increase in water is so insignificant we don't worry about it. Yeah. If you want to talk hydronium ion, we're not going to do that. But what would you like to talk about? Correct. Correct. Exactly. Yep. But remember that, yeah, that's there, but okay, I heard you talking about hydrogen. The reason that the hydroxide attacks the acetic acid is because it targets the weakest, the easiest target, and that would be the acetic acid rather than the hydronium ion. But guys, just understand, hydroxide attacks the unprotonated acid, forms more of this, and then it reestablishes equilibrium, and this goes down a little. If you want to dig into more of the chemistry later, we can. Do you guys understand the principles behind this? What questions do you have about how fundamentally a buffer functions? You're good? So I'm not asking you to I'm just asking you to trust that this is how it works. That's all you got to do, just because this is how it works. You guys okay with how it works? Okay, so guys, here's what we're going to do. We're going to call timeout. This was all a review of what you learned last time. So now we're going to call timeout, and we're going to talk about some of the additional things that you need to understand about buffers. One is capacity. How much acid and how much base can a buffer absorb before it finally fails or breaks? We're going to talk about that. Then we're going to talk about the effective pH range of buffers. This is going to take us about 5 minutes. Once we've then figured out those two ideas, then we're going to come back to this idea of how buffers function, but we're going to treat it mathematically rather than conceptually through the lens of an icebox. You ready to move on? Okay, so guys, let's first of all, I think capacity is first. Let me check. Yeah, so guys, let's talk capacity first. So when we talk about capacity, and I'll give you notes in a second, but let's talk about it conceptually first. When we talk about capacity, the question that we're asking is this: how much hydrogen can we throw into this buffer before the buffer finally just fails? Or how much base can we throw into this buffer before the buffer just finally fails? So now that you understand what capacity is about, let's answer the question, and let's do it with an acid first. Guys, let me ask you differently. What determines how much acid you can add to a buffer? Go ahead. Oh, sorry, Anna, go ahead. Exactly. Guys, the answer is, how much acetate do you have? Does that make sense? No, don't. Yeah, sort of. Yeah, you can go limiting reactant. So, but guys, put this together as a sentence. How much acid can you put in a buffer? How much acetate ion do you have? Because as soon as you've added more hydrogen ions than you have acetate ions, then there's no more acetate to soak up the hydrogens and the buffer fails. Does that make sense? So what about the other way? How much hydroxide can you add to a buffer? As much as acetic acid as you have. Does that make sense as well? Okay, so then guys, let's turn this into something you can sort of sink your teeth into. So when we talk about buffers, and you may want to write this down, when we talk about buffers, there are two important factors that you need to understand. First of all, capacity. So guys, capacity is defined as the amount of acid or base that a buffer can absorb, how's this for a good word, without an appreciable change in pH. We know that the pH is always going to change a little, but at what point will it change as if it weren't a buffer? And we've already identified that the answer to that question is, how much of the thing that's absorbing the acid or the base do you have? So let's talk about a couple scenarios. You guys all caught up with me? You okay? So guys, we understand that this depends on the amount of substance that the buffer is made of. The more weak electrolyte we have and the more conjugate salt we have, the more effective the buffer will be. So let me show you an example. For example, this. Imagine that we make a buffer that is 1 molar in acetic acid and 1 molar in sodium acetate. Then imagine that we make another buffer that is 0.01 molar in acetic acid and 0.01 molar in sodium acetate. You guys are all writing this down, aren't you? Can we talk about it? Because if you're writing, you're not going to understand the concept. Are you okay with the idea? So guys, we've got 2 different buffers. Let's call this buffer number 1. So buffer number 1 is 1 molar in each component. Buffer number 2 is 0.01 molar in each component. You ready for an interesting question? What will the pHs of these 2 buffers be? Buffer 1, buffer 2, what will their pHs be? The same. Why will their pHs be the same? Well, guys, remember the chemistry. 1 molar, 1 molar. If the concentrations are the same, what's the pH? pKa. 0.01 molar and 0.01 molar. If the molarities are the same, what will the pH be? pKa, right? And guys, this is the same weak acid, acetic acid. So in both of these examples, pH will be equal to pKa. And because they're both acetic acid, they have the same Ka values. So both of these will have exactly the same pH. Does that make sense? Okay. But then, guys, what about this? Which one of these will be the better buffer? Which one will have the greater buffering capacity? 1 or 2? 1, right? And how many times more? 100 times more. Because this is 1 molar, that's 100th molar. So the top buffer will be 100 times more effective because it contains 100 times more stuff. You get the idea? So guys, fundamentally, the idea is the more stuff that you make a buffer out of, the more effective the buffer will be. But understand that doesn't have to create a change in pH, because you can make ineffective buffers and very effective buffers with the same pHs, because we understand that if the molarities are the same, then pH is pKa. You get the idea? You okay with the idea of capacity? Okay, so moving along then, guys, we understand, of course, then that the first solution will have the greater capacity. All right, so now let's talk about effective range. There are a couple things in this you may want to jot down. So guys, when we talk about the effective range of a buffer, what we're talking about is how far will the pH move before the buffer breaks. So pH range is understood to be the range of pHs over which the buffer can effectively absorb hydrogens and hydroxides. Now there's a guiding principle in this that I need to share with you. Buffers, guys, are most effective when the concentration of the 2 components are about the same. So the weak acid or base and the conjugate salt. Buffers are most effective when their concentrations are about the same. So when the concentration of HA is about equal to the concentration of the conjugate base ion, buffers tend to work the best.
Because the acids take the conjugate salt and change it to whatever it was.
Yeah.
If it was not equal, it would be more effective. If it was, you say it's most effective.
Right, right.
But if you knew it was just going to be like a buffering acid, if you increase the one with it.
Right, so you're saying if you knew that the only thing this buffer was going to counter was the attack of an acid, couldn't you just add more conjugate base salt to? Yeah, do you understand Mark's question?
It's like an industrial application.
But understand, in that case, you technically don't need a buffer. What you really need is just a jug of sodium acetate. You know what I'm saying? So there is some logic to that, but really in that instance, what you're really trying to do is you don't need a buffer because you don't care if it can't go the other way. So why not just take only the conjugate salt in that example? The other reason that that gets a little tricky is because it's hard to figure out the pH. Right? If you needed it, what you'd essentially be doing is just figuring out the pH of the weak salt sodium acetate. So it's a different conversation because buffers are necessarily understood to be able to absorb both. Does that make sense? Okay, so guys, let's remind ourselves though, because we're about to get into something interesting. Remember what we've just said, that buffers are most effective when the concentration of the weak thing is about equal to the concentration of the common ion. But guys, what magic thing happens when these two concentrations are the same relative to pH? What is pH equal to? pKa. That is about to become important because here's what we've said. When we're building buffers, we want to build them so that this is true. Buffers work the best when the two concentrations are about the same. But when the two concentrations are about the same, pH is equal to pKa. And that provides us a really interesting thing that we can take advantage of. But guys, first of all, this. What does it mean when we say about the same? Well, guys, let's be a little more clear than that. Guys, when we say about the same, what we're talking about is a factor of 10. So if one of these becomes 10 times more concentrated than the other, then the buffer loses its effectiveness. But guys, this is where we then get into an interesting logarithmic idea. So the idea is this. If we've got HA in equilibrium to A minus and H plus, when we write the Kc expression for this, we understand that it's product divided by reactant. So this is our Kc expression. So what we're saying is this. If this becomes 10 times more concentrated than this, so if this becomes 10 times bigger, or if this becomes 10 times bigger than the A minus, then the buffer's not as effective. So if this becomes 10 times bigger, we end up with a ratio of 10 over 1. If this becomes 10 times bigger, we end up with a ratio of 1 over 10. So if either of those ratios occur, where this becomes 10 times bigger or where this becomes 10 times bigger, if you get in either one of those situations, the buffer becomes ineffective. But what does that have to do with pH? Well, guys, the idea is this. Let me see if I can erase a little bit of this so you can read it. Guys, the idea is this. If we've got a situation where this is 10 times bigger than that, that's 10, right? 10 over 1 is 10. The log of 10 is 1. If we end up in the other situation where the denominator is 10 times bigger, the log of a tenth is negative 1. So what we've said is this. If this is 10 times bigger, or if this is 10 times bigger, that range of concentration values causes a range of pHs of plus or minus 1. So fundamentally then, what we can say is this. For a buffer to be effective, buffers are usually effective when their pH range is pKa plus or minus 1. And guys, we come up with that plus or minus 1 because plus or minus 1 is representative of those concentration changes of being 10 on either side of equal. So now some of you are going, what the crap does that mean? So let me show you what this means. Imagine that you've got our good friend acetic acid buffer. So say that we buffer this thing and we create an acetic acid buffer. So if this molarity is equal to this molarity, so if their molarities are the same, what's the pH? pKa. And guys, you probably don't remember, Ka for this is 1.8 times 10 to the negative fifth. So if those molarities are equal, the pH of this will be 1.8 times 10 to the negative fifth, and take the log, and need a couple decimal places. So guys, the pH of this will be 4.74. You understand that all I did was took the negative log of the Ka? Okay, so if we build this buffer and if these molarities are the same, the pH will be 4.74. So now the question is if we build this buffer, over what ranges of pH would we expect this buffer to be able to be effective? And the answer would be from 3.74 up to 5.74. That's what we're saying. So the idea is, because buffers lose their effectiveness when their concentrations get out of whack by a power of 10, and because powers of 10 are representative of logarithms that are either 1 or -1, and because when the concentrations are equal, which is ideal, pH is equal to pKa, then the effective range of a buffer is actually pKa plus or minus 1. So in the example of our acetic acid, if the molarities are equal, which is ideal, the pH is 4.74, but we would expect that buffer to still be okay from 3.74 up to 5.74. Does that make sense? Yep. Not yet. So the buffer hasn't failed, but the buffer has lost its ability to function well as a buffer. And you're going to see this in lab, Mark. What you'll see is that if we took this, and as we get closer and closer to the point at which the buffer fails, the pH will start rising faster and faster and faster. And then it finally does fail, and it goes right through the roof. So this range of pHs is somewhere down in here. It's still functioning fairly effectively as a buffer. Outside of that range is where it really starts to change rapidly. Yeah, it's not the failure point, but it's approaching it. Yeah. So guys, you understand capacity and you understand pH range? All right. So now, gang, I-race boxes. You ready to roll? Goes like this. So what do I-race boxes allow us to do? I-race boxes, guys, allow us to study this chemistry mathematically. This is where we started. We talked about the idea that buffers have increased concentrations of both of these, and they respond in one fashion by absorbing hydrogens, and they respond in another fashion by absorbing hydroxides. Now, guys, we've got to define something important before we can get into the math. Where did that hydrogen come from? Where does that hydrogen come from? Strong acid, not the acetic acid. So guys, if you're picturing this, what we're talking about is set up a buffer. So you set up the buffer by taking a bucket of vinegar, dumping in some sodium acetate, boom, you've got your buffer. But once the buffer is established, when we start talking about this, what we're talking about is dumping hydrogen ions into the buffer. And where do those hydrogen ions come from? Strong acids. And guys, this is a lovely thought. All of the acids that we are going to add to buffers will be strong acids. Why is that helpful and important to understand? What do strong acids do? They completely ionize. And guys, where does this hydroxide come from? Only strong bases. In this class, You only have to be able to understand and calculate the effect of strong acids on buffers and the effect of strong bases on buffers. You will never titrate buffers with weak acids or weak bases. Thank goodness, because if you did, you'd have two competing equilibria, and it gets crazy. So guys, all that we need to worry about is adding strong acids to buffers and strong bases to buffers. But again, let's remind ourselves, to be clear, what is important about the idea that they're strong? They completely ionize. So guys, watch. This is critical for you to understand I-race boxes. The idea is this. Let's do acids first. As we add a strong acid to the buffer, because you got to understand this. As we add a strong acid to the buffer, every molecule of this that we add grabs a hold of a molecule of this and turns it into that. That is not an equilibrium process. This is strong acid kicking butt on this and turning it into this. This is not an equilibrium process. This is a quantitative, full-on, strong acid, attacks the conjugate base, converts it into this. There's no equilibrium. This is quantitative, getting it done chemistry. You get the idea? Then guys, down here, when we add a strong base to the buffer, this is also not an equilibrium process. This strong base destroys the acetic acid. For every molecule of this that we add, one of these turns into one of those. It is not equilibrium. It is a strong chemical reaction, and every one of these turns one of these into one of those. No equilibrium involved. Do you get the idea? Why is that important to understand? Well, guys, you want to get this in your notes. Let's talk I-race boxes. So here's the deal, guys. Let's talk about I-race boxes. So we are now going to talk quantitatively about how buffers respond to the addition of acids and bases. I really think you're going to want to write this down. Yeah, this is the last of this is worth writing down. So guys, here are the assumptions that we're going to make. We are now going to talk about this chemistry. What a mess. We're going to talk about what happens when we add strong acids and strong bases to buffers. Now, in order to have this conversation, we've got to make two assumptions. Assumption number one is the buffer hasn't broken. If the buffer is busted, none of this works. Now, guys, let's remind ourselves, when do buffers break? When do they break? When they run out of whatever component is reacting. So if you add a strong acid, the buffer, well, remember, guys, if you add a strong acid, the buffer breaks when you run out of acetate. If you add a base, the buffer breaks when you run out of acetic acid. So we are simply assuming that the buffer hasn't broken. But technically, Jake, what you said is also correct, that we can predict that range by going plus or minus 1 from pKa. Then, guys, number two, the other assumption that we are going to make is that the acid or base reacts, and this is an important word, completely with the buffer. That's the point. That assumes that this is strong. It's good you made that connection, Brandon. That's exactly the point. That, guys, thank goodness that this is true. Thank goodness that the acids and bases that we are going to add to these buffers do react completely. Because if they didn't, then we would have an equilibrium interacting with another equilibrium, and good night, that would get complicated.
These are the assumptions we have to make for creating I-race boxes.
Correct, but understand that in the context of AP, these assumptions will always be the reality. Okay, so guys, don't write this down now, but let me again make sure, we're now going to talk about I-race boxes, but let me make sure that you understand the idea. And I know you're sick of seeing this, but humor me one more time. This is good for you. Here we've got acetic acid. Here we've got acetate ion. Here we've got protons. Guys, when we add hydrogen to this, which way does the chemistry go? To the left or to the right? The left, yeah? So guys, the chemistry goes to the left. When that happens, does the concentration of hydrogen ion change? Not initially. So guys, this is why I'm doing this again, because we're going to understand this as a two-step process. So when we add the hydrogen to the buffer, does this change initially? No. And what kind of chemistry is it when we add the hydrogen to the buffer? It is not equilibrium chemistry. It is strong, on one molecule of this turns one molecule of this into one molecule of that. You get the idea? Then part two. Why does this then eventually change? Because it goes back to equilibrium. Can you see that? So guys, eventually what happens is when we're done attacking the buffer with the acid, this will have gone up and this will have gone down, right? Because this got converted into that. How much of this got converted into that? However much of this you added. Be careful, Rebecca, it's not 5%. Guys, hear this. How much of this gets converted into this? The answer is, how much of this did you add? Right? So guys, when we attack the buffer, the acid converts this into this. How much? How much is that did you add? But notice that as that chemistry takes place, this doesn't change initially. But then why does it change? Goes back to equilibrium. This goes up, this goes down because of the attack. Once the attack is over, it goes back to equilibrium. And if this is up and this is down, Le Chatelier's principle says it's going to go this way, and then it's going to make more hydrogen ion. And that is an equilibrium process. So guys, this is what ice boxes let you do. It lets you break this down into two steps. Step number one is not an equilibrium process. It's the strong acid kicking butt on the buffer. Then step number two is the equilibrium process. As the new this that got made goes back to equilibrium and makes a little bit of hydrogen ion. And guys, that's the way we're going to conceptualize this. Step one, strong chemistry butt kicking. Step two, the reestablishment of equilibrium that creates a little more hydrogen ion. You get the idea? So what does that look like in an ice box? Here's how this works, guys. Write this down with me. So what happens, guys, is this two-step process then becomes what we call an I-race box. And it goes like this. Part one is the acid-base neutralization that takes place. But guys, this is not an equilibrium process. It is a particle-dependent, every hydrogen ion that goes in kills an acetate, turns it into acetic acid. This math has got to be done in moles. Because moles is how we measure particles. And every particle of hydrogen that goes in kills an acetate and turns it into an acetic acid. So this chemistry has got to be done in moles. This is the I and the R in the I-race box. It is the initial amount and the amount that is reacted. This is the butt kicking as the strong acid or base whoops up on the buffer. But then, guys, once the carnage is over, Then we get to some equilibrium chemistry. So what we're going to do then is we're going to take Ka and we're going to take our newly adjusted concentrations of weak acid and conjugate base ion. We're going to take these from step 1. And we're now going to talk about a new equilibrium that gets set as the buffer allows itself to go back to equilibrium. But guys, this equilibrium is a molarity-dependent concentration because equilibrium is a molarity situation. It's a concentration situation because it is dependent upon rate and Le Chatelier's principle, not dependent upon strong chemistry, which we do in moles. So this gives us our adjusted, our change, and our new equilibrium conditions. So guys, we're going to solve a couple of these. If the words seem muddled or misleading or just unclear, wait until you see the math. And I think that this will become more clear to you. So guys, I'll give you a second to write this down. You guys okay? Not yet? Can I go? Anybody going to be really upset if I switch pages? You guys okay? Okay. So guys, this is the way these read. I think it would be worth your writing this down. At least the data, because this page is going to go away. These take a lot of space to solve. It says this. It says a buffer is made by mixing 100 milliliters of 1 molar acetic acid with 100 milliliters of 1 molar sodium acetate. We already know the Ka of acetic acid is 1.85, or 1.8 times 10 to the negative fifth. And then it says calculate the pH of the solution, and that actually shouldn't be a question mark. It's probably better represented as a series of dots. So calculate the pH of the solution when? Y'all caught up with me? You okay? So guys, let's do this first. Let's calculate the pH of the solution right now. What's the pH? 4.74. I'm done. You? We already did it, right? How do I know it's 4.74? Well, the molarity of the let me switch colors. The molarity of the acetic acid is right there. The molarity of the sodium acetate is right there. Because those molarities are equal, pH is equal to pKa. The Ka is 1.8 times 10 to the negative fifth. We already took the negative log of that. We already know it's 4.74. You guys okay with that? Okay. Now guys, this. What will the pH of this system be when we dump 50 milliliters of hydrochloric acid into it? That's where this starts to get tricky. This is where we're going to start to incorporate a I-race box. So guys, here's how you're going to do this. Do it with me. Of course, these are going to be bigger than ice boxes because you've got 2 additional lines. And you're going to find out spacing is really important. Don't write until you see me do it. But guys, when you're building an I-race box, so the first thing that you need to do is build all of this on the buffer. So what is HCl a part of our buffer? No, HCl is what we're using to attack the buffer. So guys, our buffer goes like this. CH3, COOH, in equilibrium. I would encourage you to write the conjugate base ion first, like so. So there's our buffer. Now guys, what we need to do next, and I would strongly encourage you to do this, before you get into doing any math, it is worth your time to identify the chemistry that's going to take place. So, to this buffer, are we adding an acid or a base? An acid. And guys, I would really encourage you to do this. Here's what I like to do. I like to remind myself that I'm adding an acid, so I write a proton above the equilibrium arrow. Then, as we've been representing this chemistry, are we going to end up with left-moving or right-moving chemistry? We're going to be going this way. So that is what the addition of the acid will do to the buffer. You guys comfortable with that? Okay, now guys, please don't write this down until I'm done. Frankly, I struggle with remembering how to space this out. So I need to think through it in front of you. So guys, we now need to build our I-race box. So we're going to go I, R, where do I put the A? Okay, A, yeah, A, C, I want to go a little bit lower. Okay, so A, C, E. So guys, when you go ahead and do it now, when you build your I-race box, skip a line between the R and the A. You'll thank me later. Okay, now guys, what I'm about to write up here on the board, you don't need to write down when you're doing this like on the tests, but I want to put this in context for you. So guys, I-race boxes allow us to break the chemistry into two parts. Part number one is right here. This is, you'll see. This is the neutralization. This is the equilibrium. Now guys, let's talk. Looking at our balanced equation, where is the neutralization represented? In what color? What color is the neutralization represented in? Red. Guys, the neutralization is the strong acid attacking the acetate and turning it into acetic acid. That is the neutralization. And guys, you got to understand, this happens one molecule at a time. Every one of those that you add kills one of those and creates one of those. It is no messing around, no equilibrium, full-on chemistry. Now guys, the equilibrium process is the blue process, because after the neutralization has happened, then the buffer goes back to a new equilibrium. So how do we treat that mathematically? Well guys, the deal is this. When you start in the neutralization, this chemistry has got to be done in moles. This is not an equilibrium process. This is a strong chemistry process. And it's got to be done in moles. So guys, initially, how many moles of acetic acid do we have? No. No. We don't know. We have to calculate it. Here's what we do know. We know that we have 100 milliliters of 1 molar acetic acid. Guys, we have to calculate how many moles. You will do this off to the side. I'll do it on a clean screen. It goes like this. 100 milliliters we want to know how many moles of CH3COOH. So 1,000 milliliters is 1 liter. 1 liter is 1 mole of CH3COOH, because that's the molarity. So we have 1/10 of a mole, 100 divided by 1,000 times 1. Is that right? So we have 0.100 moles of CH3COOH. You okay with that? By the way, guys, let's just do the math right now. The other thing that we need to know is how many moles of acetate ion we have. The same, right? Because we also have 100 milliliters of 1 molar sodium acetate. So you should do the math again. 100 milliliters, 1,000 milliliters, do the math. Yeah.
So here when we express that it's a pKa.
We're not even talking about equilibrium yet. So guys, here's what we've established. What we know right now is that we have initially 0.100 moles, not molarity, moles. 0.100 moles of this, 0.100 moles of this, and no moles of hydrogen ion. You guys okay? Okay. Now, guys, let's talk. Why does this need to be in moles? Here's why. What is eventually going to happen to this buffer? Well, we're going to drop a strong acid into it. And guys, this strong acid, for every molecule of that goes in, one of these is going to go down and one of these is going to go up. So guys, how much of this is going to get converted into that? What's the answer? How much HCl did you add? How much HCl did we add? 50 milliliters of 1 molar. So now we got to do another calculation. So our third calculation will be 50 milliliters, and we need to know how many moles of HCl. So 1,000 milliliters is 1 liter. 1,000 milliliters is 1 liter. 1 liter, it's also 1 molar, right? Is 1 mole. Oh, check me, guys. 0.0500. Is that right? Okay. So let's just call it 0.05. So guys, we are adding 0.0. Is that right? 0.05? Okay. So guys, we are adding 0.05 moles of HCl, right? So we are adding 0.05 moles of this. So watch my finger, how much of this is going to get turned into this? 0.05 moles. So what does that mean? Well, that means that this will go down by 0.05 moles. And what's going to happen to this? It's going to go up by 0.05 moles. What's going to happen to hydrogen? Nothing. So now, guys, the question is, how much is left? Well, do the subtraction. 0.1 minus 0.05, that leaves us with 0.05. And guys, notice where I'm writing this in the skipped space. 0.05 moles are left there. How much of... No, that's addition. Sorry, this is 0.05 moles left. This is 0.15 moles created. Yes? Okay. So guys, look at what happened. Think about the chemistry. We started with 0.1 moles of each of these in the buffer. Then we added the strong acid, and every stinking molecule of acid that we added turned one of these into one of those. And finally, we stopped adding acid. So in the end, we added 0.05 moles of acid. This went down by 0.05. That went up by 0.05. Now we're done. The carnage is over. The buffer did its thing. It absorbed the acid. Hydrogen hasn't changed. This has not wiggled. So now what does the buffer do? Reestablishes equilibrium. Now, guys, this is important to understand. Equilibrium is not a quantitative process. Equilibrium is a rate-based process, right? When we study equilibrium, we don't need moles. What do we need to know? Molarity. So guys, what we've got to do is we've got to convert these moles into molarity. But how do we convert from moles to molarity? What do we need to divide by? The volume. What's the volume? Good. Where'd you get, is it? Yeah, 250. Because we started with 100 milliliters of this, 100 milliliters of this. We added 50 milliliters of this. We now have 250 milliliters of solution, which is 0.250 liters. Do you see why I had you skip a space? 0.250 liters. And then obviously we don't have to divide 0. So this is 0. And then guys, 0.15 divided by 0.25 is 0.60 molar. 0.05 divided by 0.25 is 0.20 molar, and then 0. Did I do that right? Oh, good. All right. So now, guys, we've got some brand new molarities, don't we? We started with 1 molar of each of these, but some of it got consumed. So now we've got our new volumes. And guys, now what we need to do is we need to figure out the new equilibrium conditions. So what do? This is just like the good old days. Minus x, plus x, plus x. This would be 0.60 minus x. This would be 0.20 plus x. And this would be x. How are we doing? So now, guys, how do we turn this into a pH? What do we need? Ka expression. So, oh boy, this is where my board is limiting, but we'll do it anyway. So we've got this. We've got Ka is equal to CH3COL minus, hydrogen plus. Oh, I knew that was coming. Hydrogen plus, and CH3COH. So we've got 1.8 times 10 to the negative fifth, and then we had is equal to, was it 0.2? Okay, so 0.20 minus x plus times x divided by 0.60 minus x. And then guys, remember we need to do approximately equal to 0.20 x divided by 0.60. And now we do the math 0.8 times 10 to the negative fifth times 0.6 divided by 2. So x is then equal to, I get 5.4 times 10 to the negative fifth. You buy that? Is that okay? Then guys, pH is equal to the negative log of hydrogen ion is equal to the negative log of 5.4 times 10 to the negative fifth. This is molar. So we take the negative log of that, change the sign, and I get 4.27. Which? Did I do something wrong? Am I okay? Am I okay? Okay. So guys, think about what just happened. Where did this buffer start? What was its pH? 4.74. And we dumped in 50 milliliters of 1 molar hydrochloric acid. Guys, you get that on you, you're done. That is ridiculously strong hydrochloric acid. And look what it did to the pH. It changed half a pH step. It went from 4.7 to 4.2. 4.3, really. It hardly changed at all. Guys, that's the magic of a buffer. A buffer can absorb that attack of the hydrochloric acid without its pH changing much. We just demonstrated that mathematically. You get the idea? So guys, now let me throw this at you. Imagine if we reset the scenario, but now we did this. Instead of adding an acid, we added a base. 50 milliliters, again, of 1 molar, again, but now it's a base. So guys, do this with me. Hold on, do this. How does this change? What happens? So now this is OH. What direction are we moving now? To the right. So how will that change things? Will the first line be the same? Will the second line be the same? The signs change. This will become a minus and this will become a plus because now the base is driving the chemistry in the other direction, so this will be made and this will be consumed. But after you change those signs, everything else is the same. And then, of course, it would also change this math. But guys, fundamentally, the only difference between adding an acid and adding a base is when you add a base, this now goes down and this goes up, but everything else is fundamentally the same. Yeah. In the other direction. Yep, exactly. Yep, you got it. What do you think, y'all? Tons of chemistry, huh? Guys, here's what I want you to do. I want you to plant a mental flag in your brain right now. And remember not only what you just learned about buffers, but remind yourself, remember how you learned it. And then when you get to college and you have a university professor try to teach this to you and 500 of your closest friends, drop me an email and just say, thanks. Because guys, you have no idea how complicated they can make this in college. Come back to this. Guys, don't do it the way they try to teach you. Guys, come back to this. Remember, it's simply just an equilibrium that's being disrupted by a strong component. Draw the arrows, place the things above the equilibrium symbol. Use an iRace box, regardless of how they teach it to you. Guys, I promise you, this foundation will serve you well throughout your college career. So, guys, we're done. These are the fundamentals of titrating buffers. Of course, now the trick is you need to go practice.